we are looking at permutations with ordered elements. Now, non-ordered elements. Now, if you remember, permutations means order matters. So non-ordered elements, reading the word non-ordered elements with permutations should give you pause for a second. If it doesn't, well, just know that it probably should. But we're going to explain what we mean by that. Okay, so the first thing we want to look at is how many ways can you arrange A1, A2, and B? And I just wrote them out here. There's basically 6 factorial ways to arrange them, which is 3 times 2 times 1. Oops, I meant 3 factorial ways, which is equal to 6. Okay. And essentially it's right there. But if we write them out and remove these subscripts right there, we get AAB, AAB, etc., etc. Now, these are the same, right? There's 2 factorial ways, or 2 ways to arrange AA within the same grouping, right? So there's 2 factorial ways to arrange it. And what we end up with is 3 possible ways. We'll talk about that more in a second. But we're going to do this example where we try comparing A1, A2, A3B, and AAB. So when we look at AAB, how many ways is there to arrange the triple A's and the B's? Well, there's basically, when we have B as the last digit, well, there's 3 factorial, 6 ways to arrange it. When we have B as the third character, well, there are 6 ways to arrange all the A's with keeping the B in the same spot. And once again, we move B to the second place, and we see that there are 6 ways to arrange all the A's, again, around this B. And finally, using the B as the first digit, we see that there are 3 factorial ways to arrange the A's. Now, in total, how many ways are there to arrange A1, A2, A3, and B, assuming they're different? Well, there's 4 factorial ways. Okay. Basically, but there are 4 ways to arrange A, triple A, B, right, with no difference. Now, is there a way to calculate that? And how can we think about that? Of the 4 factorial ways to arrange this, there is 3 factorial ways to arrange A1, A2, and A3. So the way you solve it is we kind of use this. This is a little bit confusing when you read it, but I'll explain it to you. So, and I'll apply it to the last example. The number of permutations of n elements, n over there, where p of one type are identical, p of one type are identical, and q of another type are identical, q of another type, and r of another type are identical, and so on, for all identical statements. That is the number of permutations that you can arrange certain things with. Now, how does that apply? So if I have A, B, well, I have 4 items. N would be equal to 4 in this case. And in this case, P, as it's defined in this formula, would be equal to the number of elements that are identical, 3, right? Now, if I had BB, right, 4 identical items, then Q would take into effect, and Q would be equal to 4, right? So it would be 4 factorial, or sorry, in this case, we'll change it again. There's 7 items, so it's 7 factorial over 3 factorial times 4 factorial. And where does the r come into play? Well, we don't have a third type, so we don't even take it into consideration. Okay, so if you want, you can write that formula down. Let's apply it to there. How many ways are there to arrange AAAB? Well, there's 4 factorial over 3 similar items, 3 factorial, which is equal to 4. So, example 2, a soccer team has 5 wins, 2 losses, and 7 ties. How many ways could this have happened? So, if we write it out, we got 5 wins, 2 losses, and 7 ties. So we have 1, 2, 3, and it doesn't even have to be all in a row, right? 1, 2, 3, 4, 5, 6, and 7. So we have a total of that many games, 14 games. So how many ways can you arrange these? 5 wins, 2 losses, and 7 ties. Well, you take the total, 14, and you have 5 of the same W's, 2 of the same losses, and 7 ties. When we put that into our calculator, that becomes 72,072 ways. Let's move on to example 3. In how many ways can you arrange the word Hamilton if the vowels must remain in the same order? So I have these vowels, A, I, O, but also they can be separated A, I, O. Okay. The total number of permutations of Hamilton is 8 factorial. And there are 3 that includes arrangements where A, I, O is out of order, right? And that there are 3 factorial ways to arrange those vowels. Since I don't want to count those, I treat them like objects, and it's 8 factorial over 3 factorial, which is 6720. Okay, so I'm going to explain this a little bit better. Okay, so I have Hamilton. And I'm going to rearrange this. Basically, I'm going to write it over here. This is homework. Consider this 3.1, do these questions. But I'm going to explain that right now, what I mean by that. Hamilton. Okay? I wish there was a way to Hamilton. Hamltn. Hltn. I'm going to write it 6 times. HMLTN. And I think one more. And let's fix that a little bit. Let's clean it up. LTN. Now, these are 6 different arrangements. It's the same arrangements of Hamilton, right? But I can arrange this as in AOI, right? I can arrange it where this is, that's out of order, by the way, out of order. That's OAI, and that's OIA, out of order, right? And then I can put I's here and put AO or OA here, and that'll be out of order. So for every single item, there's only one way it can be in order. And because there are 3 items to arrange, if we don't want to count these, if order doesn't matter, well, there's 3 factorial ways to arrange it. I just divide by 3 factorial, right? So it's 8 factorial divided by 3 factorial, because for every single way, right, to arrange Hamilton, right, for example, this way, MAHILTON, right? It's just a little bit different, but there are 6 ways to arrange that where A, I, and O are out of order. So for every one of them, that's why I divide by 3 factorial. Okay, that's all.